as Eugene said, I've done quite a lot of work on energy harvesting so far. In fact, most of the work I've done in my research career so far is for energy harvesting. But one of the things that you get very used to when you're looking at energy harvesting, particularly applying it to wireless sensor networks, is trying to see and do a calculation as to how much energy can you harvest and how much energy does your sensor node need. And often it's quite difficult to make these things meet in the middle. And so that led us to start thinking about other ways of making autonomous wireless sensor networks, which got around this issue of can you do more with the sensor node by having more power, but yet not have to have batteries for replacement or need to tether the sensors in some way. They need to remain wireless. So this led us on to looking at autonomous sensing networks using drones. And essentially, as I just suggested, the difficulty often with wireless sensor networks, I think it's something that's still discussed a lot more than actually ends up being deployed, partly because where you want to use them is often a harsh environment. That's difficult in terms of construction of the devices, and it's difficult in terms of maintaining the amount of power that you need and maintaining communications in an environment which can be quite noisy with such low power available for the communications. And energy harvesting and then mesh networking has gone some way to solving these problems. But as I've said, the amounts of power you can get from harvesting tend to be really quite limited. Depends, of course, specifically on the application, but in many cases it's very limited. That limits the amount of power you can put into the communication protocols and the distance that you can get. And it almost always prohibits you from doing any actuation. And if you want to do actuation, then you probably need to move on to something that is capable, of delivering more power than an energy harvesting solution can deliver. And so what I want to present to you today is this concept of a synthetic sensor network as being a way of overcoming some of these traditional issues that we see with the wireless sensor network powered by energy harvesting. And this really is inspired by synthetic aperture radar. And synthetic aperture radar, for those of you not familiar with it, is a technique where you can get improved resolution from radar, not by increasing the aperture size of the radar, but in this case by moving a fixed aperture around, in this case attached to an aircraft, in order to be able to get more information about a larger area or increase the resolution over a smaller area. So what does that mean in terms of moving this onto the wireless sensor network? Well, we can basically employ drones as being something which can move around the network. That means that these drones could potentially get very close to certain sensors. They could then read data from those sensors, and they can then basically backhaul the data physically by moving around the network and connecting to some other network system at a different location. While they're doing that, of course, then they're able potentially to inject some power into the actual sensor nodes. So there's a means of injecting potentially quite significant power, in this case using some sort of wireless power transfer solution onto the nodes. And if we do this right, then we might be able to get significantly more power capability in the nodes than we would be able to with a traditional energy harvesting solution. So clearly there are some technical challenges here. We've got to think carefully about the communications, but we've got to think very carefully about the power optimization and how we inductively charge a fixed object from a platform which is mounted on a drone and which is therefore moving, and we're not able to control exactly. And so I'm going to basically discuss through some of the technical challenges and show you some demonstrations of what we've been able to achieve in this synthetic sensor network concept. So just to show you this video, this is basically the concept. We've got a drone. It's got some form of wireless transmitter on the front there. It's able to charge a sensor network, and the sensor is transmitting data back, and there's some sort of communication that's happening between the drone and the actual sensor itself. So from a technical perspective, then, what I'm going to talk about, I will show you a brief proof of concept of some of this that we've tried on campus at Imperial, including some basic data transfer from the drone to these nodes. But I'll spend most of the talk talking about the issues that we've had to solve in terms of wireless power delivery, because I think, after all, this particular session is based on power supply for wireless sensors, so I'm going to concentrate on that in particular. And I think it's quite a difficult scenario in which to operate wireless power transfer. for the reasons I mentioned. You've got to have a lightweight system because you're flying it on a drone. You've got to transfer power quickly because the drone shouldn't spend very long next to one of these sensors. And it's got to cope with a reasonably large air gap and an air gap which is moving all the time because you can't make the drone hover as close as you would like. So then I'll show you some video demonstrations of all of this actually working. So just to show you very briefly proof of concept for the data transfer aspect of this, we started doing this with a Mitcheson 100 drone. If anyone's played with drones in any of your research, you may well have used this particular model. It's quite good. You can bolt stuff onto it. You can modify it quite easily. And we were using these Telos B sensor nodes for this first trial. These are nodes that were, I think they were designed in UC Berkeley. They're probably over 10 years old now in terms of the design, but they're perfectly fit for purpose here. And we then had one of these sensor nodes mounted underneath the drone and a bunch of these sensor nodes that were then spread among the Imperial College campus. And you can see here, very simple test network that we set up with 3 nodes on this area in Imperial College called Queen's Lawn. The big tower there is called the Queen's Tower. Incidentally, it's about the only thing that's left of the original Imperial College. And so we were able to fly this drone around and collect data. And you can see here that what was happening effectively was that these sensor nodes were collecting data. In this case, I think they were sampling on something like a 20-minute basis. And then every couple of hours, the drone was able to fly around and collect this timestamped data. And therefore, we've basically formed our wireless sensor network, but we've only needed very, very low power communication because we've brought the receiver very close to the actual sensor nodes themselves. There were some practical problems that we had to overcome to make this basic test setup work, and I guess we should have thought about these much earlier than we actually did. We had some problems because the actual communication link between the drone and the sensor node was operating at 2.4 gigahertz, but actually our controller between the person controlling the drone and the drone itself was also at 2.4 gigahertz. So we had to play around a little bit to move the frequency band for the controller in order to enable the communication to work properly between the drone and the sensor node. But effectively, we've proved the basic principle. We can move this drone around and we can collect data from a bunch of wireless sensor nodes. Okay, so let me now talk about the bit that I think is the real technical challenge here, which is making the wireless power delivery aspect of this work. And as I mentioned, if you can make wireless power delivery work in an inductive system like the one shown here, then you can potentially transfer quite large amounts of energy in quite short periods of time. And this means that essentially as your drone is able to fly around your sensor network, you can dump quite a lot of energy quickly into a sensor node and potentially then have an overall average power consumption on the sensor node that is actually quite a lot in excess of what you could do if you were using an energy harvesting device. So for those of you not familiar with wireless power delivery, you can see here the simple setup. You've got a transmit coil on the left and a receive coil on the right, and you create magnetic flux from the primary at high frequency, links with the secondary, and you're able to transfer power wirelessly. So many of you may have an electric toothbrush, and that's probably one of the most common wireless power solutions that you may come into contact with. And some of you may have Qi-enabled mobile telephones. So what is it that makes this more challenging than the Qi-enabled wireless charged telephone or the electric toothbrush? Well, fundamentally, we need to have significantly larger range between the transmitter and the receiver because it's not going to be possible for the drone to exactly hover in the right place right next to the sensor node. And also, of course, that air gap is going to be changing quite considerably. You're not going to be able to hover in a very precise position. So we've got to create a system here which, of course, has to be lightweight because it's going to be flown on a drone. We've got to have a high link efficiency. In other words, our transfer of energy from the flying drone here to the stationary object has got to be very efficient because we can only carry a certain amount of energy around on the flying drone. In order to achieve that, we need to have an optimal reflected load between the receiver and the transmitter to make sure that that is done in an efficient way. And we need to maintain then, of course, high circuit efficiency for all parts of the system. So if we just look at the state of the art, perhaps, of some existing systems so far that are available with wireless power delivery, then you see here various things appearing in automotive, and people are looking at very high power transfer capability for charging electric vehicles. And people are also then looking on the other end of the spectrum, as I mentioned, at low power for things like the Qi standard for charging mobile phones. And certainly maybe this is something that might gain a little bit more traction now than it's had. I know Apple has recently, with the new iPhone, has jumped into the wireless charging space. But the issue, I guess, with all of these scenarios is that they tend to be quite heavy for the amount of power that they can deliver, and the range tends to be quite limited. And the reason for that is that they tend to focus on increasing the coupling factor between the coils rather than making the coils high Q factor. So I'll tell you a little bit about our approach to how we make wireless power links and how we make them light and how we make them long range, which is different to what people are doing commercially. So you can see here, this is just a test setup in the lab where we're looking at power transfer between two coils, looking particularly at what happens as we vary the coupling factor between the coils. So the governing equation for the link efficiency for a wireless power transfer system is this equation at the top here. And you can see that it is dependent on the square of the coupling factor between the coils and the Q factor of the individual transmit and receive coils. So as long as your product of K squared, Q1, Q2 is high, you don't really care whether it's high because Q is high or because K is high. And if you can maintain K squared, Q1, Q2 and up at around 10 to the 3 here, then you can see that you can get pretty high wireless power transfer efficiencies between the two coils. And traditionally what people have done is tried to increase the value of K, and that makes this wireless power link look more and more like a transformer. In other words, you're trying to get tight coupling between the coils. But if you want to get good distance between the coils, you can't really push K to be very high. Fundamentally, if you want to have a long range, you have to have the system operating with a low value of K. And if that's the case, you've got to push up the value of Q. So if you push up the value of Q, you can do that fairly simply by operating at high frequency. I say fairly simply, the basic theory of that is very simple because the Q factor of the inductor is approximately given by omega L over R. So if you push up omega, you get a high Q factor. If you push the frequency too high, then the coil will start to radiate, and then it will be inefficient. And so you need to keep somewhere below the radiation corner of the curve. And for the sorts of coil diameters that we're typically talking about with these systems, that might be a few centimeters to a few tens of centimeters, it typically means that the operating frequency for these systems ends up being in the low megahertz range. And we try and stick in ISM bands, so that means typically 6.78 or 13.56 megahertz. So there are then some technical challenges we have to overcome, particularly then on the circuitry for the transmitter in order to make this work. We're now talking about making circuits that have to process potentially quite large amounts of power. If this is going to be a useful sensor network, in the sense that we need to only visit with our drone these nodes on a very periodic, fairly intermittent perhaps basis. In other words, we only visit them for a short period of time, once every hour or perhaps once every day, then we need to be charging these sensors at tens of watts if they have a power consumption perhaps in the low milliwatt range, in order to enable long degrees of autonomy without the drone having to constantly come back and recharge the system. So this means that we have to build very lightweight circuitry, and lightweight ultimately means high efficiency so that we don't have to have large heat sinks on it to cool it down. Operating, in this case, at multiple megahertz, able to transfer around, say, 100 watts. Conventional solutions for doing this in power electronics don't typically scale very well into the megahertz range. So anybody that's got experience or knowledge of building switch mode power electronic circuits, simple things like buck or boost converters, they can be quite efficient, but typically they only operate in the tens to hundreds of kilohertz range. If you want to push these systems into the megahertz, you basically have to have the devices being soft switched. In other words, you need to make sure that when a transistor changes state from being on to being off, it does so in the most lossless way possible. In other words, we need to have the current in that device or the voltage across that device zero during the point where the device switches. And that's possible with some types of of DC to AC inverter topology that would be suitable for connecting to the transmit coil in this particular case. There's an example circuit there. This is quite a common circuit that is used in high-frequency wireless power delivery at this point. Class E inverter circuit. Very simple because it's only got one transistor, and that also is potentially good, again, for lowering the weight and the cost of this type of device. And you can see here that the voltage across, the drain of the transistor goes to 0 at 2 points in the cycle, so you can turn the transistor on under 0 voltage and you can turn it off under 0 voltage. And that means that you can operate this type of inverter very efficiently at very high frequency. So the switching loss is absolutely minimized. But the problem with this is that you can only tune it to operate to be 0 voltage switched at one particular point. And with certain wireless power transfer systems, this may be okay. With something like your electric toothbrush, there's a very good known coupling between the toothbrush and the charging base as you locate it in a very specific point. The same with the Qi standard. There's probably going to be a very well-known coupling factor between the transmitter and the receiver because you physically place the receiver onto the transmit pad. But in this system where we've got a flying drone, we've got very variable coupling factors, and therefore back through the turns ratio of the wireless power system, that means we get a different reflected load onto the transmitter, and that will then move you, as you can see, away from soft switching. And that means that we lose efficiency and potentially means that we could damage the transmit side. So we've looked at trying to solve that problem, and we had a breakthrough a couple of years ago. I think this is an application which benefits from this, but I think all wireless power transfer systems, if they're going to be practical, they need to be able to cope with air gaps which are dynamically changing. And this circuit is a solution to that problem. Simply, it's the Class E circuit, but with an additional parallel branch there of C2 and L2. And I'm not going to go, obviously, into the specific details of the operation of this circuit. But what this additional branch enables here is it gives you sufficient degrees of freedom in the circuit design that you're able now to cope with the value of RL here changing, which will happen as the distance between the coils changes, whilst maintaining soft switching over the entire range of operation. So when I showed these graphs 2 slides ago, you could see that the 0 voltage switching had been lost. Here you can see that the voltage across the transistor slightly changes shape, the trajectory changes, but the 0 voltage switching points stay in the same place. And so that additional network gives us the opportunity to design the circuit in such a way that we maintain 0 voltage switching as we change the reflected load. And you can see that there in operation, taken directly from the oscilloscope. The yellow is the drain voltage on the transistor, and it's changing as we, in this case, change the distance between a transmitter and receiver. But fundamentally, the nice thing is that the points where the transistor turns off and turns on remain 0 voltage switch, so we get very high efficiency. So that's our solution on the transmit side. We have similar sorts of problems to look at on the receive side, and in this particular case, we're looking at a topology where we can receive this high frequency. We then have a supercapacitor bank because we want to be able to very quickly charge up a receiver as the drone flies past. So we need some interface between the rectifier and a bank of supercapacitors. And then there's going to be a step-down converter on the output of that supercapacitor feeding the load. And that load, hopefully, is then only going to be typically a milliwatt or maybe significantly less than a milliwatt as this sensor node is operating in the background before the drone then comes back again to pick up the data and to recharge it. So the rectifier itself, in order to make the link, the wireless link, as high efficiency as possible, has to show the correct reflected load back onto the transmit side. So there's an optimal reflected load back through the link to get the maximum efficiency, and that depends on the link geometry, and it also depends on the properties of the rectifier. And so we've looked at how we build the rectifier to do that, and we've looked at several different topologies of rectifier. We've then tried to make sure that the rectifier and the supercapacitor charger are obviously well integrated in terms of voltage levels. And what we've tried to do in this demonstration is, whilst the rectifier design is custom, we've tried to make sure that the rest of this is able to be built using regular off-the-shelf circuitry. So we looked at a couple of different rectifier topologies, and There's a simple Class D rectifier at the top here, current source driven, and a full, a full wave version at the bottom there. And one of the problems with this type of circuit is that you cannot control what the reflected load to the transmitter looks like independently of the actual load resistor that is present on the system. And we can't really control that. So what we need is an additional degree of freedom again in order to be able to effectively change the reflected load back onto the transmitter to make sure it's optimal, independent of this value of load resistor on here. And we can do that by using a Class E type of hybrid type of rectifier. Again, I'm not going to go into the circuit details on this, but this is something that we patented recently, and you can see on the front end here there's effectively a capacitor divider, so you've got a combination of a series and parallel resonance here, and that enables you to change the reflected load and gives you an additional degree of freedom on top of what's happening with your actual load resistor. Okay, so we've then got attached to that at the output of the rectifier the circuit which charges the supercapacitor, and that we've measured has, in this case again, as I said, it's an off-the-shelf part, has an efficiency of about 93%. We've then got our supercapacitor bank, which in this case is 3 farad 5.4 volt supercapacitors in series, and that means that if we charge this in just a couple of seconds, then in this case we can store more than 130 joules into this system. And then the output stage of this that's actually powering the sensor node is an off-the-shelf Texas Instruments buck converter chip, and the efficiency of that again is above 90%. So that's effectively what goes into our system, and a lot of, as I mentioned, a lot of the effort here goes into designing something which is lightweight, and the advantage of operating at high frequency is you get the lightweight capability, but also being able to design circuits that are able to work with large air gaps and varying air gaps. So you can see here, here's our drone, here's a wireless sensor node sitting on top of this box, which is represented at the moment with just an LED attached to the system, and you can see here that we're able to take our wireless coil in the proximity of our receiver, transfer some energy across, and we're able to then run this lamp for however long we've got based on the fact that we charged it with 130 or so joules. So that's part of the system in place. We're able to now fly a drone around and charge a receiver. But if we want to make the system completely autonomous, then we also need to be able to wirelessly charge the actual drone itself. So we started looking at actually charging the drone. And again, the difficulty here is that you need to make something that's very lightweight. Particularly in this case, if you're going to start putting a wireless power transfer system onto this drone, what that is effectively going to be doing is eating into the amount of weight that's available for actually putting the battery onto the system. And so we started off looking at wirelessly charging a very small drone, and you can see here a drone flying above a wireless charging pad. You can see that the drone here has got its receiver wrapped in copper foil wrapped around the guard ring around the propellers, and this drone is actually flying with absolutely no battery or supercapacitor on the system at all. We basically had to take that away, replace it with a wireless power system in order to balance the weight of flying the drone, but we are able to fly it here, basically flying in a magnetic field with no battery at all. So then we thought, well, can we use a drone to charge a drone? So we tried that. So here you can see, here's our original large drone with its wireless power transmitter on it. And in the middle here is a drone similar to the one I just shown you, but now with, in addition, some supercapacitors on it. Our drone pilot needs a little bit more practice by the looks of it. But that drone was completely discharged before we started this video, and what you now see is we've squirted enough energy onto that drone, and we've got a wireless power receiver on that drone and supercapacitors, and we're able to fly it for, in this case, about 10 seconds, just from squirting charge into it for a couple of seconds. Okay, so just to wrap up then, what I've presented here, I think, is a bit of a quirky but new paradigm for wireless sensor networks that we're calling synthetic sensor networks. It enables us to use an autonomous drone system to visit a bunch of remote sensors and exchange data and at the same time transfer power to those sensors. And some of the advantages perhaps of this are that you can then rely on only short-range communication, so it might be particularly good in certain types of harsh environment. You potentially open up the ability, as I've just shown there, to have some form of actuation on the receive side, because we're able to now transmit much more energy to the system than you could do, than would be achievable with a simple energy harvesting type solution. There are a bunch of technical challenges that we had to overcome, and that was really associated with making the system very lightweight and making it work with varying air gaps over a fairly long range. And just to give you a sort of headline figure for what's achievable here, we're able to transfer power here at over 50 watts. So if the average node consumption is 1 milliwatt, that means that our duty cycle is about 0.002%, which turns out to be about 7 seconds of charging for every hour of use. So thank you very much for listening.